Hello everyone and welcome back. I am Mr. Cobalt, and in this video I'm going to go over a couple of problems where you are going to be using the enthalpy of the reaction to help you use stoichiometry to solve a problem. So the first problem is you have an LP gas tank, and inside the LP gas tank you have 13.2 kilograms of protein, sorry. And this is the kind of gas that you're going to be using like when you're cooking on barbecue. So you've got 13.2 kilograms of protein, you've got your balanced equation, and you also have the delta H of the reaction given. And they want to know how much heat is going to be produced from the burning of this amount of propane. So the first thing you're going to do is given the fact that you've got a balanced equation, that should tip you off that you're going to be using stoichiometry, which means you're going to be using your mole-mole ratio or something like that to solve this problem. And so, because they want to know the amount of heat, you're going to have to use the stoichiometric amount of whatever amount they give you, using that in conjunction with the coefficient. So you can convert from an amount of kilojoules to moles of anything in the equation. Since we're interested in propane, right? So here we want heat. So we want to go from the amount of propane that they gave us to an amount of heat. So we're going to start with the mass of propane. So they give us 13.2 kilograms of propane, C3H8, over 1. And now we're just going to convert, because in order to get to kilojoules, we need to get to moles, because we can use the kilojoules to mole ratio as a conversion factor. So we need to get onto the mole-mole ratio. Remember the chemistry conversion superhighway, going from mass to moles of A to moles and mass of B. So we need to get onto that highway, if you will. So we got kilograms, we want grams. So again, we're going to use the 1 kilogram is equal to 10 to the third grams. So 1 kilogram of C3H8 on the bottom, 10 to the third grams of C3H8 on the top. So kilograms. So now we got grams. So now we can use the molar mass of propane to go from mass in grams to moles. So if we calculate that really quick, we get 3 times 12.011 plus 8 times 1.008 equals, and that gives us, so we get 44.097 grams of C3H8, and that is going to be moles on the top of C3H8. So grams cancel out, and now we have moles. So now we have moles of our propane. So now we can use the mole to the delta H of the reaction, the enthalpy of the reaction, as a conversion factor. So for every 1 mole of propane burned, we're going to produce this amount of kilojoules. So now we can get kilojoules of heat. So 1 mole of C3H8 on the bottom, and negative 2,044 kilojoules on the top. So moles cancels out. We've got our kilojoules, which is what they want. So now all we need to do is calculate. So we're going to take 13.2 times 1,000 times negative 2,044. We're going to divide by 44.097 equals, and that's going to give us a negative 61,000 or 611,851.1463 kilojoules. Alright, so now we need to pay attention to our sig figs. We have 3 sig figs here. This is exact, so we can ignore the sig figs. It's infinite. Here we have 5 sig figs. Here we have 4 sig figs. So the least number is 3. So we're going to have to cut it off here. We have an 8 there. So it's going to end up being 612,000 kilojoules of energy produced by that amount of propane. Okay, so that's how you do it. So you can see that we've gone from a mass of propane all the way to kilojoules using conversion factors just like we've done before. The only difference here now is now we can use the relationship between moles of a substance in your balanced equation and kilojoules of energy released using your enthalpy of the reaction. Okay, so what about this problem here? So in this case, we're combusting or burning butane. So here we're given 1.5 times 10 to the 3 kilojoules of heat produced. So we've burned a certain amount of butane and it produced this much heat. Okay, so the first question is, what is the mass of butane that was needed to produce this amount of butane? So we want mass in grams. Okay, so what you can do is, again, we're going to start with heat this time. So we're going to start with 1.5 times 10 to the 3rd kilojoules of heat. And we want grams of butane. But in order to get to grams of butane, we need to get to moles of butane first. And so in order to get to moles, we need to use our delta H of the reaction and our balanced equation. So we're interested in moles of butane. So if we can get to moles of butane, then we can continue on to grams. So we can use the butane, this is butane, so we know that 2 moles of butane is related to negative 5,312 kilojoules. So we can use that as a conversion factor. And so kilojoules is on top, so I'm going to put negative 5,000, and this is going to be negative because this is the amount of heat produced. Since heat is produced from the reaction, it's negative. So negative 5,316 kilojoules for every 2 moles of butane, C4H10. So kilojoules cancel out. Now I have moles of butane, and so now I can convert that to grams using the molar mass. So the molar mass of butane can be calculated fairly quickly. So I have 4 carbons, so 4 times 12.011, plus I have 10 hydrogen, so 10 times 1.008 equals, and so the molar mass is going to be 58, so 1 mole of C4H10 is to 58.124 grams of butane, C4H10. Now I have grams, moles cancels out, and so now I can just calculate the number of grams. So I'm going to multiply 58.124 times 2, multiply that by negative 1.5 times 10 to the 3 divided by negative 5,316 equals, and that gives me 32.80135 yada yada yada, and that's going to be grams of butane. Now I need to figure out sig figs. So what are the sig figs? So I have 2 sig figs here, I have 4 here, and I have 5 here. So least number is 2, so I'm going to have to cut it off at the 2. So I have an 8 here, so this is going to round up to 33 grams of C4H10 butane. So that would be the necessary amount. So I need to burn 33 grams of butane to produce this amount of heat in kilojoules. So that's the grams of butane. The next one is, what is the mass of carbon dioxide produced? Well, since I know the grams of this, I can convert from grams to moles again. Or what I can do is I can just do the same thing here. So I would do, say, negative 1.5 times 10 to the third kilojoules over 1. Use the same conversion conversion factor to convert to moles of propane. Or in this case, instead of propane, they want mass of carbon dioxide. So I can convert directly to carbon dioxide using the ratio of this amount of kilojoules to 4 moles of carbon dioxide. So let's do that. So I have kilojoules of energy, that's going to be related to 4 moles of carbon dioxide. So kilojoules cancels out. Now I have moles of carbon dioxide, and now I can use the molar mass of carbon dioxide, which is going to be, let me double check, it's going to be 12.011 plus, it's going to be 32, yeah, 44. So it's going to be 44.011 grams of CO. Oops, that should be on the top. So 1 mole of CO2 is going to be the 44.011 grams of CO2. Moles cancels out. I left with grams. And so now I can calculate that. And so that's going to be, let's calculate this quickly, 1.5. Oops. So it's going to be negative 1.5 times 10 to the third times 4 times 44.011 divided by negative 5,316 equals, and that gives me 49.6738 grams of carbon dioxide. And again, I gotta watch out for my sig figs. So I have 2 sig figs, I have 4. This is an exact number, 4 moles. And then I've got 5 here. So the least number is 2 again. So I'm gonna have to cut it off here. So 6 is there, so I gotta round this to 50. So 50 grams of carbon dioxide is produced from this reaction. So as you can see, I can use very easily the amount of heat evolved or absorbed by the reaction using the enthalpy of the reaction as a conversion factor in relation to any substance that I have here using the coefficients as mole ratios. Okay, so I hope this was helpful. I hope this makes sense. If you like this video, share this video, hit the notification bell so you can be notified of other videos, hit the subscribe button, and make a comment in the comment section. Let me know what you think, and if you have any other questions you want me to cover. Thanks for joining me, and I'll see you next time.